Tonight, we drift through mysteries written in starlight, through a galaxy that turns without asking permission, keeping secrets older than Earth itself. Above you right now, even if clouds hide it, even if city lights drown it out, the Milky Way stretches across darkness like a river of forgotten stories. That pale band you sometimes glimpse on clear nights, it's only the surface. Behind that soft glow lies a collection of facts so strange, so unexpected, that even astronomers who study it every day still find themselves surprised. The Milky Way isn't just our home. It's a cosmic puzzle box, and tonight we're opening it together. 100 facts, 100 revelations, each one pulling back another layer of mystery. Before we begin, if you find something interesting here tonight, a gentle like or subscribe would mean everything. It's a small thing, but it tells me someone out there is listening, learning, drifting through these cosmic mysteries alongside me. Now settle in, get comfortable, and let's start counting down these mysteries, beginning with the most basic question of all. For thousands of years, people looked up at that band of light and had no idea what they were seeing. Nobody understood the truth, which is both simple and profound. We live inside the galaxy. We're embedded so deep in one of its spiral arms that seeing its full shape is like trying to understand the layout of a city while standing in the middle of a crowded intersection. The view is blocked by what's closest to you. This is our first mystery. We couldn't see our galaxy's shape for most of human history. Think about that for a moment. Every civilization that ever existed, every person who ever looked up at the night sky, they saw that pale band of light but couldn't grasp what it meant. They made up stories, created myths, assigned divine significance to it. But the simple truth that we were looking at our own galaxy from the inside remained hidden until very recently in cosmic terms. The person who first glimpsed the truth wasn't even a trained astronomer. William Herschel was a musician in the late 1700s who taught himself astronomy as a hobby. He was an organist and composer living in England, performing concerts and teaching music to make a living. But at night, his passion turned to the stars. He built his own telescopes, grinding the mirrors by hand in his basement, a painstaking process that could take months for a single mirror. Some of his telescopes were enormous for their time, with mirrors over a foot across, far larger than anything commercially available. Herschel didn't just observe the sky casually. He conducted systematic surveys, spending night after night counting stars in different regions. This was tedious work, requiring enormous patience and dedication. Imagine standing outside in the cold English night, eye pressed to a telescope, counting faint points of light one by one, writing down numbers by candlelight, then moving to another patch of sky and doing it all again. He did this for years, building up a database of stellar positions and counts that nobody had attempted before. He would point his telescope at different regions of the sky and simply count how many stars he could see, trying to find patterns in their distribution. Were there more stars in some directions than others? Did the density change as you looked toward different parts of the Milky Way's band? His sister Caroline worked alongside him, recording his observations and doing calculations. Together, they mapped the heavens with a thoroughness that was unprecedented for their era. What Herschel discovered was revolutionary for its time. Stars weren't scattered randomly across the heavens, like someone had thrown them there. They formed a flattened disk, a structure with width and depth but relatively thin height. Imagine a dinner plate covered with grains of sand. That's closer to the truth than a sphere or a random cloud. He found that stars were much more numerous when he looked along the plane of the Milky Way than when he looked perpendicular to it, suggesting we were inside a flattened structure looking edge-on at our own system. This was the first real evidence that our collection of stars had a definite shape, that the universe had structure and organization. It meant the Milky Way wasn't just a random scattering of lights, but an actual physical system with geometry and boundaries. But Herschel couldn't see the spiral structure. The dust and distance prevented that. He saw only the disk, and even that discovery was groundbreaking enough to change astronomy forever. He published his findings, and though not everyone accepted them immediately, his work laid the foundation for our modern understanding of galactic structure. The next major breakthrough came more than a century later, and it completely transformed our understanding of the universe itself. In the early 1900s, astronomers were studying mysterious cloudy spirals scattered across the night sky. They called them spiral nebulae, assuming they were just clouds of gas within our own galaxy. But there was a debate. Some astronomers suspected these spirals might be much farther away than anyone imagined. Edwin Hubble settled the question in 1924. Working at Mount Wilson Observatory in California, he used the 100-inch Hooker telescope, the largest in the world at that time, to study one of these spirals called the Andromeda Nebula. He was looking for a specific type of star called a Cepheid variable, stars that pulse with a regular rhythm. The rate at which these stars pulse is directly connected to their true brightness, which means you can use them as cosmic measuring sticks. By comparing how bright they appear to how bright they actually are, you can calculate their distance. When Hubble measured the distance to Andromeda, he got a number that shocked the astronomical community. Andromeda wasn't a nebula within our galaxy. It was roughly 1 million light-years away, far beyond any reasonable boundary of the Milky Way. This meant Andromeda was another galaxy entirely, a system of billions of stars existing separately from our own. And if Andromeda was a spiral galaxy, vast and distant, then our own Milky Way was probably a spiral too. The next major breakthrough came more than a century later, and it completely transformed our understanding of the universe itself. In the early 1900s, astronomers were studying mysterious cloudy spirals scattered across the night sky. They called them spiral nebulae, assuming they were just clouds of gas within our own galaxy. But there was a debate. Some astronomers suspected these spirals might be much farther away than anyone imagined. Edwin Hubble settled the question in 1924. Working at Mount Wilson Observatory in California, he used the 100-inch Hooker telescope, the largest in the world at that time, to study one of these spirals called the Andromeda Nebula. He was looking for a specific type of star called a Cepheid variable, stars that pulse with a regular rhythm. The rate at which these stars pulse is directly connected to their true brightness, which means you can use them as cosmic measuring sticks. By comparing how bright they appear to how bright they actually are, you can calculate their distance. When Hubble measured the distance to Andromeda, he got a number that shocked the astronomical community. Andromeda wasn't a nebula within our galaxy. It was roughly 1 million light-years away, far beyond any reasonable boundary of the Milky Way. This meant Andromeda was another galaxy entirely, a system of billions of stars existing separately from our own. And if Andromeda was a spiral galaxy, vast and distant, then our own Milky Way was probably a spiral too. This discovery fundamentally changed humanity's place in the cosmos. We went from thinking our galaxy was the entire universe to realizing we lived in one galaxy among countless others. The universe was suddenly unimaginably larger than anyone had conceived. It's hard to overstate how revolutionary this was. Imagine thinking you lived in the only city on Earth, and then suddenly discovering there are millions of other cities, each with billions of inhabitants, scattered across distances so vast you can barely comprehend them. But confirming that our own galaxy had a spiral shape took decades more work. The problem is simple to state, but incredibly difficult to solve. When you're inside a spiral galaxy, it's almost impossible to see the spiral structure clearly. Dust and gas block your view of distant regions. Stars crowd the foreground, making it hard to see what's behind them. The perspective is wrong, the angle's skewed. It's genuinely like being in the middle of a dense forest and trying to figure out the shape of the entire forest. You can see trees immediately around you, but understanding the overall pattern is nearly impossible. Scientists had to piece together the Milky Way's structure like archaeologists rebuilding a broken pot from scattered fragments. They mapped the positions of young, bright stars, which tend to cluster in spiral arms. They traced the distribution of hydrogen gas using radio telescopes which could peer through the dust that blocks visible light. They measured distances, velocities, temperatures, building up a picture piece by piece over decades of patient observation. NASA's Spitzer Space Telescope, launched in 2003, provided crucial data by observing in infrared light. Infrared penetrates dust clouds more effectively than visible light, allowing astronomers to see through the murky regions that block our view. These observations revealed the structure of our spiral arms more clearly than ever before. Then, the European Space Agency's Gaia mission, which began in 2013, took this to another level entirely. Gaia is mapping the precise positions and motions of over 1 billion stars, creating the most detailed three-dimensional map of our galaxy ever made. What emerged from all this patient work was a portrait of our home. The Milky Way is a spiral galaxy roughly 100,000 light-years across. It has either 4 major arms or 2 major arms and 2 minor ones, depending on how you count. This might sound odd, but astronomers genuinely disagree about the exact number. The difficulty comes from our position inside the structure and from the fact that spiral arms aren't solid objects but density waves where matter temporarily bunches up. Think of spiral arms like traffic jams on a highway. When you're driving and you hit a traffic jam, the jam itself stays in roughly the same place, even though individual cars are constantly moving through it. Cars enter the jam from behind, slow down, then speed up again as they exit the front. The jam persists even though it's made of different cars at different times. Spiral arms work the same way. They're regions where stars, gas, and dust temporarily bunch together as they orbit the galactic center. The density wave rotates more slowly than the stars themselves, creating a lasting pattern we can observe. This density wave theory was proposed by astronomers C.C. Lin and Frank Hsu back in the 1960s. They worked out the mathematics to explain why spiral patterns persist even though individual stars move at different speeds. When a star or gas cloud enters a density wave, it slows down slightly because of the increased gravitational pull. This compression is what makes the spiral arms visible. The slowing causes gas clouds to compress, which triggers star formation. New stars are born in these compressed regions, and because young stars are hot and bright and blue, they illuminate the spiral arms, making them stand out against the background. Here's something interesting about those young stars. They don't live long enough to leave the spiral arms where they were born. The most massive stars, the ones that burn the brightest blue, only live a few million years. That sounds like a long time, but it's nothing in galactic terms. By the time these stars die in supernova explosions, they're still within the spiral arm where they formed. This is why spiral arms appear blue in photographs of other galaxies, while the regions between them look yellower and redder. The blue color comes from young stars still being born, while the yellow and red colors come from older, longer-lived stars that have had time to drift away from their birthplaces. Our Sun sits in a minor arm called the Orion Spur, sometimes called the Orion Arm or Local Arm. We're nestled between two larger structures, the Perseus Arm and the Sagittarius Arm. This minor position might actually have been crucial for life on Earth. The major spiral arms are sites of intense star formation, which means frequent supernova explosions. These explosions release deadly radiation that can sterilize planets across dozens of light years. By residing in a quieter spur between major arms, we're protected from the worst of this violence. The entire galaxy rotates, but not like a solid disk spinning on a turntable. Different parts rotate at different speeds, which is part of what creates and maintains the spiral structure. The Sun takes roughly 225 to 250 million years to complete one orbit around the galactic center. Astronomers sometimes call this a galactic year, and it's a useful way to think about cosmic timescales. Consider this. In the time since dinosaurs walked the Earth, roughly 65 million years ago, the Sun has only traveled about 1/4 of the way around the galaxy. We're still in roughly the same spiral arm where the dinosaurs lived and died. In the time since our solar system formed 4.6 billion years ago, we've made about 20 complete orbits around the galactic center. That's our cosmic odometer, 20 laps around the galaxy since the Sun first ignited and began fusing hydrogen into helium. We're moving at roughly 514,000 miles per hour as we orbit the galactic center. Let that sink in for a moment. 514,000 miles per hour. To put that in perspective, that's about 700 times faster than a commercial jet aircraft. It's fast enough to circle the Earth's equator in less than 3 minutes. Yet you feel absolutely nothing. No wind, no acceleration, no sense of movement whatsoever. This is because we're carried in perfect harmony with everything around us. The Earth, the Sun, all the nearby stars, the gas and dust in our neighborhood, we're all moving together like dancers in a slow waltz, all keeping the same rhythm. When everything moves together at the same speed in the same direction, relative motion disappears. It's the same reason you don't feel the Earth spinning beneath you, even though the surface at the equator is moving at over 1,000 miles per hour. You, the air, the ground, everything is rotating together, so there's no sensation of movement. But we're not just orbiting the galactic center. We're also bobbing up and down through the galactic plane, like a horse on a carousel. The Sun oscillates above and below the midplane of the disk, completing one full oscillation every 60 to 70 million years. Right now, we're slightly above the midplane, moving upward, and in about 10 million years, we'll reach the peak of our oscillation before falling back down through the plane. Some scientists have speculated that these passages through the galactic plane might expose Earth to increased cosmic ray bombardment or gravitational disturbances from giant molecular clouds, possibly triggering climate changes or even mass extinctions. The evidence for this is debated, but it's a reminder that our motion through the galaxy isn't just abstract astronomy. It potentially affects the environment of our planet over geological timescales. The galactic center, that bright bulge you sometimes see in photographs, is crowded with older stars packed into a spherical region. These stars are far more densely distributed than in our neighborhood. If you could stand on a planet near the galactic center, assuming you could survive the radiation environment, the night sky would be spectacular. There would be millions of stars visible to the naked eye instead of the few thousand we can see from Earth. The sky would never truly get dark. Beyond the visible disk, our galaxy is surrounded by a halo of globular clusters. These are ancient groups containing hundreds of thousands of stars each, orbiting far above and below the flat spiral. They're some of the oldest structures in the galaxy, formed over 13 billion years ago, when the Milky Way itself was just beginning to take shape. These clusters orbit the galactic center in elongated elliptical paths, sometimes plunging down through the disk and then soaring back up into the halo. They provide a three-dimensional framework around the flat spiral, like a spherical shell partially surrounding the disk. Recent discoveries have shown that the galactic disk isn't perfectly flat either. It warps and bends like the brim of a hat that someone has bent. This warp becomes more pronounced farther from the galactic center, where the disk's outer edges curve up on one side and down on the other. The warp is possibly caused by gravitational interactions with satellite galaxies, smaller galaxies orbiting the Milky Way that tug on the disk's outer regions. Think of it like a vinyl record that got slightly warped in the heat. It still spins, but it's not perfectly flat anymore. Now let's talk about what sits at the very heart of our galaxy, because this is where things get truly strange. For decades, astronomers suspected something massive was lurking at the galactic center, hidden behind immense clouds of dust and gas. Stars near the center moved oddly, orbiting an invisible point in space at speeds that defied explanation. Something with tremendous gravitational power was pulling them, something that produced no light whatsoever. In the 1990s, two teams of astronomers began a patient observational campaign that would eventually earn them the Nobel Prize. Reinhard Genzel in Germany and Andrea Ghez in California independently started tracking individual stars near the galactic center, watching them orbit this invisible point year after year. Some of these stars completed orbits in just over a decade, which is incredibly fast for stellar orbits. They were moving at a significant fraction of the speed of light, thousands of kilometers per second. The only thing that could produce this kind of motion was a supermassive black hole. By carefully measuring the orbits of these stars, both teams calculated the mass of whatever they were orbiting. The answer was stunning. At the center of our galaxy sits a black hole with a mass 4 million times that of our Sun, compressed into a region smaller than our solar system. They named it Sagittarius A star, pronounced Sagittarius A star after the constellation where it resides. Let me put that mass in perspective for you. Imagine taking our Sun, that brilliant burning sphere that warms our days and makes life possible, and somehow compressing it into a point smaller than Earth. Now multiply its mass 4 million times. That's the scale we're dealing with. The gravitational well is so deep, so intense, that nothing can escape once it crosses the event horizon, the point of no return. Not matter, not light, not even information in the quantum mechanical sense. One particular star, called S2, has been studied extensively because its orbit brings it very close to Sagittarius A star. S2 completes its orbit in just 16 years, which might sound like a long time in human terms, but it's extraordinarily fast for stellar orbits. For comparison, it takes our Sun 230 million years to orbit the galactic center once. S2 orbits the black hole millions of times faster in proportion to the mass it's orbiting. In the 1990s, two teams of astronomers began a patient observational campaign that would eventually earn them the Nobel Prize. Reinhard Genzel in Germany and Andrea Ghez in California independently started tracking individual stars near the galactic center, watching them orbit this invisible point year after year. Some of these stars completed orbits in just over a decade, which is incredibly fast for stellar orbits. They were moving at a significant fraction of the speed of light, thousands of kilometers per second. The only thing that could produce this kind of motion was a supermassive black hole. By carefully measuring the orbits of these stars, both teams calculated the mass of whatever they were orbiting. The answer was stunning. At the center of our galaxy sits a black hole with a mass 4 million times that of our Sun, compressed into a region smaller than our solar system. They named it Sagittarius A star, pronounced Sagittarius A star, after the constellation where it resides. Let me put that mass in perspective for you. Imagine taking our Sun, that brilliant burning sphere that warms our days and makes life possible, and somehow compressing it into a point smaller than Earth. Now, multiply its mass 4 million times. That's the scale we're dealing with. The gravitational well is so deep, so intense, that nothing can escape once it crosses the event horizon, the point of no return. Not matter, not light, not even information in the quantum mechanical sense. One particular star, called S2, has been studied extensively because its orbit brings it very close to Sagittarius A star. S2 completes its orbit in just 16 years, which might sound like a long time in human terms, but it's extraordinarily fast for stellar orbits. For comparison, It takes our Sun 230 million years to orbit the galactic center once. S2 orbits the black hole millions of times faster in proportion to the mass it's orbiting. During its closest approach, S2 comes within about 11 billion miles of the black hole's event horizon. That sounds like a safe distance, but in cosmic terms, it's incredibly close. That's roughly the distance from our Sun to Neptune, the outermost major planet in our solar system. At this closest point, S2 is moving at roughly 3% of the speed of light, which translates to about 20 million miles per hour. That's an absolutely mind-boggling speed for something with the mass of a star. At these extreme velocities and in such an intense gravitational field, relativistic effects become visible and measurable. Time itself runs slower for S2 during its closest approach, exactly as Einstein's general relativity predicted over a century ago. This isn't science fiction or theoretical speculation, it's measurable reality. The star's light gets stretched and shifted in ways that match Einstein's equations with remarkable precision. Astronomers have actually measured this time dilation directly. They've observed how the star's light is affected by its motion and by the intense gravity it's experiencing. The wavelength of light emitted by S2 gets stretched because of the gravitational redshift, and it also gets shifted because of the Doppler effect from the star's tremendous velocity. The measurements match Einstein's predictions to extraordinary precision, providing one of the best confirmations we have that general relativity works even in these extreme conditions. But there's something else remarkable about observing S2. When it's at its closest approach to the black hole, moving at 3% of light speed, the star's image actually appears to move across the sky night by night. Astronomers can watch it change position in real time, or at least on time scales of days rather than years. This allows them to trace its orbit with incredible accuracy. By watching S2 and other stars in the galactic center year after year, astronomers have created what amounts to a cosmic laboratory for testing physics in extreme conditions. They can measure the orbit's shape, its precession as the ellipse slowly rotates in space, and all the subtle effects predicted by Einstein. Every observation confirms that general relativity works even in the most intense gravitational fields we can observe in the universe. In 2022, the Event Horizon Telescope collaboration released something truly remarkable. They produced the first image of Sagittarius A star itself. Well, not the black hole itself, which by definition emits no light, but the glowing ring of superheated matter swirling around it. The image showed a dark circle, the shadow of the black hole, surrounded by a luminous halo of doomed gas and dust. This material is spiraling inward, heating to millions of degrees through friction and compression before finally disappearing forever beyond the event horizon. Creating this image required a global network of radio telescopes working together to essentially create an Earth-sized telescope. The technical achievement is staggering. They had to coordinate observations from sites around the world, synchronize them to billionths of a second, and then process the data using supercomputers to reconstruct the image. The result showed that Sagittarius A star looks remarkably similar to M87 star, the first black hole ever photographed, which sits at the center of a galaxy 55 million light-years away. What makes this discovery so profound is the realization that supermassive black holes appear to exist at the center of nearly every large galaxy. They're not rare cosmic accidents, but fundamental components of galactic structure. Some astronomers believe these black holes actually helped shape their host galaxies, their gravity guiding the formation of stars and spiral arms over billions of years. There seems to be an intimate connection between a galaxy and its central black hole, a relationship we're still working to understand. Our galaxy's black hole is relatively quiet compared to some. Despite its immense size, Sagittarius A star consumes very little matter. It's not actively devouring large quantities of gas and stars. Instead, it sits dormant, sipping only small amounts of material that drift too close. Some galactic centers blaze with energy as their black holes actively feed, producing jets of radiation that shoot out for millions of light years. Ours mostly just waits, patient and silent. But it wasn't always this calm. Evidence from various observations suggests that a few million years ago, just a blink in cosmic time, our black hole underwent a period of intense activity. It may have consumed a large gas cloud or torn apart a star that wandered too close, producing a burst of radiation that lit up the galactic center like a beacon. Those ancient photons are still traveling outward through space, and when they strike distant gas clouds, they cause them to glow faintly, creating what astronomers call light echoes. The Fermi Gamma-Ray Space Telescope has detected these echoes as enormous structures called the Fermi bubbles. These are gigantic lobes of high-energy radiation extending 25,000 light-years above and below the galactic plane. To put that in perspective, the entire galactic disk is only about 1,000 light-years thick in our region. These bubbles are evidence of violent past activity, proof that our galaxy's heart was not always sleeping, but has periods where it blazes with terrifying energy. The black hole could wake again. If a large gas cloud or a wayward star wanders too close, Sagittarius A star could roar back to life, releasing jets of radiation that would light up the galaxy's core. We wouldn't be in danger here on Earth. We're 26,000 light-years away, far enough that the radiation would be diluted to harmless levels by the time it reached us. But the sky would change. Our ancestors might see the galactic center glow brighter, a new beacon in the night sky, where once there was only that faint band of the Milky Way. The region immediately surrounding Sagittarius A star is one of the most extreme environments in our galaxy. The density of stars there is millions of times higher than in our solar neighborhood. Here, the nearest star to our Sun is over 4 light-years away. Near the galactic center, stars pass within light days of each other, close enough that gravitational interactions are common. Some stars get flung outward at incredible speeds through these interactions, becoming what astronomers call hypervelocity stars. These are stars moving so fast they can escape the galaxy entirely, shooting out into intergalactic space. One particularly fascinating object near the galactic center is called G2. It's a dusty gas cloud about 3 times Earth's mass that passed extremely close to Sagittarius A star in 2014. Astronomers expected it to be torn apart and consumed, potentially triggering a burst of observable activity from the black hole. But G2 survived the encounter largely intact, which was surprising. This suggests it might not be a simple gas cloud, but possibly a young star shrouded in dust, something with enough gravitational self-cohesion to hold itself together even in that extreme environment. Around the galactic center, within a region about 1 light-year across, astronomers have identified a cluster of massive young stars. These are stars weighing more than 100 times the Sun's mass, and their presence is genuinely puzzling. The tidal forces near a supermassive black hole should prevent star formation in this region. The gravity is so intense and changes so rapidly over short distances that gas clouds should be torn apart before they can collapse to form stars. How these massive stars came to be so close to Sagittarius A star remains an open question. One theory suggests they formed farther out and migrated inward through gravitational interactions with other stars. Another proposes they formed in a massive disk of gas that briefly existed around the black hole millions of years ago, a kind of accretion disk from which stars could form before the gas was consumed. The truth might be some combination of these scenarios or something else entirely that we haven't thought of yet. The black hole itself is invisible, but its influence extends far beyond its immediate vicinity. It shapes the orbits of stars thousands of light years away. It creates density waves in the surrounding gas. And it may have played a role in forming the galactic bulge itself, that spherical concentration of older stars at the galaxy's center. Some models suggest that in the early universe, supermassive black holes formed before galaxies, seeding the regions where galaxies would eventually coalesce. In this view, the black hole came first, and the galaxy grew around it like a pearl forming around a grain of sand. Other models suggest the opposite, that galaxies formed first and black holes grew within them, fed by gas falling toward the center. The truth probably lies somewhere in between, with black holes and galaxies co-evolving, each influencing the other's growth over billions of years. This is one of the active areas of research in modern astronomy, trying to understand the relationship between supermassive black holes and their host galaxies. What's clear is that the relationship is intimate. Observations of other galaxies show a tight correlation between black hole mass and the properties of the galactic bulge. Larger bulges have more massive black holes, and this relationship holds across a wide range of galaxy sizes and types. This correlation suggests a deep connection, some kind of feedback mechanism, where the black hole's growth affects the galaxy and the galaxy's evolution affects the black hole. When a black hole feeds actively, it releases enormous amounts of energy. This energy heats the surrounding gas and can blow it away, preventing it from falling onto the black hole and also shutting down star formation in the central regions of the galaxy. Over billions of years, this feedback may explain why supermassive black holes don't grow indefinitely. They reach a size where their energy output prevents more matter from falling in, creating a natural equilibrium between the black hole and its host galaxy. Now, let's shift our perspective outward from the galactic center and talk about something that might surprise you. The Milky Way is not a peaceful, isolated island of stars floating serenely through space. It's actively eating its neighbors. Right now, as you listen to this, our galaxy is consuming smaller galaxies, tearing them apart, star by star, absorbing their matter into our own spiral structure. This isn't speculation or theory. It's documented, measured, and ongoing. Astronomers have discovered dozens of stellar streams, long rivers of stars stretching across the sky. Each one is the scattered remains of a dwarf galaxy that wandered too close to the Milky Way and was pulled apart by tidal forces. The European Space Agency's Gaia mission has been crucial in uncovering these streams. By precisely measuring the positions and velocities of over 1 billion stars, Gaia revealed that many stars in our galaxy are moving in coordinated groups, following paths that trace back to ancient collisions. One of the most significant discoveries was the Gaia Enceladus stream. This is the remnant of a dwarf galaxy that merged with the Milky Way about 10 billion years ago. That collision was violent enough to heat up our galaxy's disk, puffing it up and possibly triggering bursts of star formation. According to research published by astronomers at the University of Cambridge, Gaia Enceladus contained roughly 600 million times the mass of the Sun before it was consumed. Today, its stars are scattered throughout the Milky Way's halo, no longer a distinct galaxy but part of our own. But the Milky Way didn't stop there. It's still feeding. The Sagittarius dwarf elliptical galaxy is currently being torn apart. Located on the opposite side of the galaxy from us, this small galaxy has already made several passes through the Milky Way's disk. Each time it passes through, tidal forces strip away more of its stars and gas. The streams of stars from Sagittarius stretch completely around our galaxy, wrapped like ribbons around a gift. You can trace these streams across the entire sky if you have sensitive enough instruments. In another few billion years, Sagittarius will be completely dissolved. Its stars will be fully integrated into our spiral structure, and it will cease to exist as a separate entity. This is the fate of all small galaxies that venture too close to larger ones. They're consumed, their identities erased, their stars scattered and mixed with the larger galaxy's population. Then there are the large and small Magellanic Clouds, two small companion galaxies visible to the naked eye from the southern hemisphere. If you've ever been to Australia, South America, or Southern Africa and looked up on a clear night away from city lights, you've probably seen them. They look like detached pieces of the Milky Way, cloudy patches in the night sky that seem to have broken off from the main band. Ancient cultures in the Southern Hemisphere knew about them for thousands of years, incorporating them into their mythology and navigation. These are dwarf irregular galaxies orbiting our Milky Way, and they're slowly spiraling inward, doomed to eventually merge with us. The Large Magellanic Cloud is roughly 160,000 light-years away from us, while the Small Magellanic Cloud is about 200,000 light-years distant. They're gravitationally bound to each other as well as to the Milky Way, creating a complex three-body orbital dance. Recent studies using data from the Hubble Space Telescope and Gaia suggest that the Magellanic Clouds may already be losing gas and stars to the Milky Way's gravitational pull. There's a vast stream of hydrogen gas called the Magellanic Stream trailing behind them like a comet's tail. This stream stretches across more than half the southern sky, though you need a radio telescope to see it. It was discovered in the 1970s through radio telescope observations and remains one of the largest structures visible from Earth. The stream contains enough gas to form millions of new stars, material that will eventually rain down onto the Milky Way's disk, fueling future generations of star formation. It's like watching a slow-motion collision happening over hundreds of millions of years. Every orbit, the Magellanic Clouds lose a bit more of their substance, bleeding gas into space that will eventually become part of our galaxy. The Magellanic Clouds themselves are fascinating objects worth examining in detail. The Large Magellanic Cloud contains about 10 billion stars, making it a substantial dwarf galaxy. It's irregular in shape, lacking the organized spiral or elliptical structure of larger galaxies. Within it, you can find the Tarantula Nebula, one of the most active star-forming regions in our local group of galaxies. This nebula alone contains hundreds of thousands of young stars and is so bright that if it were at the distance of the Orion Nebula, about 1,300 light-years away, it would cast shadows on Earth at night. The Small Magellanic Cloud is smaller, with perhaps a few billion stars, but it's no less interesting. It has a more disturbed appearance than the Large Magellanic Cloud, possibly because of tidal interactions with its larger companion. Both galaxies are irregular in shape, which is typical for smaller galaxies. They lack the rotation and organization needed to form spiral structures. Their stars move in somewhat random orbits, creating their lumpy, asymmetric appearance. They orbit the Milky Way roughly once every 1.5 billion years, though their orbits are complex and influenced by their mutual gravitational interaction as well as the Milky Way's pull. Recent measurements suggest they may be on their first close approach to our galaxy, having fallen inward from the outskirts of the local group of galaxies. If so, their eventual merger with the Milky Way is still billions of years in the future, but the process has already begun. The Magellanic Stream is evidence that our gravity is strong enough to strip gas from these companions even at their current distance. What makes the Magellanic Clouds particularly valuable to astronomers is their proximity and their position outside the Milky Way's plane. They're close enough that we can study individual stars within them, but far enough and separate enough that we can see them as complete systems. They've been laboratories for understanding stellar evolution, star formation, and galactic structure. Many important discoveries in astronomy were made by studying the Magellanic Clouds, from variable stars that led to measuring cosmic distances to supernova explosions that revealed the accelerating expansion of the universe. This process of galactic cannibalism is not unique to the Milky Way. It's common throughout the universe, a cosmic hierarchy of gravity and time. Large galaxies grow by consuming smaller ones. Computer simulations run by astronomers at institutions like NASA's Goddard Space Flight Center show that our galaxy has likely absorbed dozens of smaller galaxies over its lifetime. Each merger adds mass, changes the distribution of stars, and can trigger new waves of star formation as gas clouds collide and compress. In a sense, the Milky Way is not a single pure entity. It's a composite, a patchwork quilt woven from the remnants of many smaller galaxies. Some of the stars you can see in the night sky may have formed in galaxies that no longer exist, their original homes dissolved into our own. Even our sun might be a second-generation immigrant. Some theories suggest the sun formed from gas enriched by previous generations of stars, possibly including material from dwarf galaxies consumed billions of years ago. The idea is both unsettling and beautiful. We are not just citizens of the Milky Way. We are descendants of lost galaxies, children of structures that no longer have names, and the cannibalism continues. The Milky Way's gravity reaches far beyond its visible disk, extending into a massive dark matter halo that encompasses satellite galaxies and stellar streams. Anything that wanders into this gravitational web eventually succumbs, stretched and torn by tidal forces until it becomes part of the larger structure. This ongoing consumption is one way galaxies grow. The Milky Way was once smaller, perhaps just a fraction of its current size. Over billions of years, it has grown through mergers, each collision adding new stars, gas, and dark matter. But there's a limit to this growth, because the Milky Way itself is not the final predator. Something larger is approaching. In about 4.5 billion years, our galaxy will collide with Andromeda, the nearest large spiral galaxy. This merger will be spectacular, a cosmic dance spanning millions of years as the two galaxies pass through each other. Individual stars will rarely collide because space between stars is so vast. Even though two galaxies containing hundreds of billions of stars each will interpenetrate, the chance of any two stars actually hitting each other is vanishingly small. Stars will pass by each other, sometimes quite close, but actual collisions will be rare. But while stars won't collide, the structures will be completely disrupted. Gravity doesn't require direct contact to have dramatic effects. As Andromeda approaches, its gravitational pull will begin to distort the Milky Way, and vice versa. The spiral arms will be pulled out of shape. Tidal forces will create long streamers of stars extending between the two galaxies. Gas clouds will collide, and unlike stars, gas clouds do compress and heat when they meet, triggering enormous bursts of star formation. Simulations created by astronomers using supercomputers show in detail what will happen. The two galaxies will approach each other over millions of years. Andromeda is currently about 2.5 million light-years away and approaching at about 70 miles per second. That sounds fast, but at cosmic distances, it means the collision is still billions of years away. The first pass through each other will be chaotic and beautiful. The galaxies will interpenetrate, their stars passing through the spaces between the other galaxies' stars. But the gravitational interactions will fling stars into new orbits. Some will be thrown outward at high speeds, ejected into intergalactic space. Others will fall toward the combined center of mass. The spiral structures will be completely disrupted, transformed into something more chaotic. Then, after passing through each other, the galaxies will separate again, pulled apart by their own momentum. But they're gravitationally bound now, doomed to fall back together. They'll swing back around for a second collision. This pattern will repeat several times over the next billion years. each collision stripping more energy from the system through gravitational interactions until finally the Milky Way and Andromeda will merge into a single giant elliptical galaxy. Some astronomers playfully call this future galaxy Milky, a combination of both names. It will be one of the largest galaxies in the local group, dominating the gravitational landscape. The spiral arms will dissolve, stars redistributed into a more rounded, diffuse shape. Any civilization existing in either galaxy at that time will have a spectacular view. The night sky will be dramatically different, filled with stars from both galaxies. By that time, our sun will be nearing the end of its life anyway, swelling into a red giant. It will grow large enough to potentially engulf the inner planets, possibly including Earth. Humanity, if it still exists, will have long since needed to abandon Earth or will have evolved or technologically transformed beyond recognition. But the galaxy that gave birth to us will also transform, losing its spiral beauty to become something new. For now, though, the Milky Way remains a spiral, still feeding, still growing, still beautiful. A cannibal wrapped in starlight, devouring its neighbors with patience and grace. The evidence of past mergers is written throughout the galaxy's structure. The thick disk, that layer of older stars above and below the thin disk where most star formation occurs, may have been created by ancient collisions. The stellar halo, containing old stars and globular clusters in orbits that take them far from the galactic plane, is thought to be composed largely of material from consumed dwarf galaxies. Even the chemical composition of stars provides clues to their origins. Stars born in dwarf galaxies often have different ratios of heavy elements compared to stars born in the Milky Way's disk. By analyzing stellar spectra, the rainbow of light that stars emit, astronomers can identify stars that likely originated in other galaxies and trace their orbits back to estimate when their parent galaxy was consumed. One particularly intriguing discovery is a group of stars called the Helmy stream, named after astronomer Amina Helmy, who identified it. These stars orbit the galaxy in a coordinated fashion, moving together like a flock of birds. This coordinated motion suggests they came from a single dwarf galaxy that merged with the Milky Way several billion years ago. Chemical analysis of these stars reveals they have lower metallicity than typical Milky Way stars, which is consistent with formation in a smaller, less evolved galaxy where fewer generations of stars had lived and died to enrich the gas. The process of identifying these ancient merger events has become a major field called galactic archaeology. By studying the motions, ages, and chemical compositions of stars, astronomers can reconstruct the Milky Way's violent history, identifying when and where past collisions occurred. Each merger leaves a distinctive signature, like geological layers in rock that tell the story of Earth's history. When a dwarf galaxy falls into the Milky Way, its stars are scattered along its orbital path, creating a stream that stretches around the galaxy. These streams gradually disperse over time as stars drift apart due to small differences in their orbits, but for several billion years they remain identifiable as coherent structures. The Sagittarius stream is the most dramatic example, completely encircling the Milky Way and wrapping around it multiple times like thread wound around a spool. The multiple wraps indicate that the Sagittarius dwarf has already completed several orbits through our galaxy, each passage stripping away more material. The stream is not uniform. Some regions are denser than others, corresponding to the current location of the dwarf galaxy's core and the locations where it passed through the disk on previous orbits. By mapping these density variations, astronomers can reconstruct the dwarf galaxy's orbital history, like reading a historical record written in stars. What makes these tidal streams especially valuable is that they're sensitive tracers of the Milky Way's gravitational field, including the distribution of dark matter. The precise shape of a stream depends on the exact gravitational forces acting on it, So by measuring stream positions and velocities with instruments like Gaia, astronomers can infer properties of the dark matter halo. This has revealed that the Milky Way's dark matter halo is not perfectly smooth. It has substructure, lumps and clumps left over from smaller dark matter halos that merged with our galaxy in the past. These dark matter subhalos can perturb stellar streams as they pass nearby, creating gaps and kinks in the stream that help astronomers map the invisible mass distribution. It's like being able to see the wind by watching how it affects leaves and dust. You can't see dark matter directly, but you can see how it affects the things you can see. The study of stellar streams has also revealed unexpected complexity. Some streams appear to have been perturbed by something massive passing nearby, creating waves and gaps in the stream. The perturber might be a dark matter subhalo, too faint to see directly but massive enough to gravitationally disturb passing stars. Alternatively, the perturbations might come from the Milky Way's spiral arms. As the density waves rotate through the galaxy, they can gravitationally nudge stars in tidal streams, creating patterns that encode information about the spiral structure's strength and rotation speed. Now, let's talk about something that might seem impossible. If you could somehow weigh the entire Milky Way, counting every star, every planet, every cloud of gas and dust, every black hole, everything that shines or glows or reflects light, you'd find something deeply troubling. The numbers wouldn't add up. All the visible matter, everything we can see or detect through electromagnetic radiation, accounts for less than 15% of the galaxy's total mass. The rest, roughly 85%, is completely invisible. It doesn't emit light, doesn't absorb it, doesn't interact with electromagnetic radiation in any way we can detect. Astronomers call it dark matter, and it's everywhere, woven throughout the galaxy like an invisible web, holding everything together with its gravity alone. The first hints of this mystery appeared in the 1930s when Swiss astrophysicist Fritz Zwicky studied galaxy clusters. He measured how fast galaxies were moving within clusters by analyzing the Doppler shifts of their light. What he found didn't make sense. The galaxies were moving too fast. Given the amount of visible matter he could see in the cluster, there wasn't enough gravity to hold them together. They should have flown apart long ago, scattered into space by their own motion. Zwicky proposed that unseen matter must be present, providing the additional gravity needed to hold the cluster together. He called it Dunkel Materie, dark matter in German. But his idea was largely ignored for decades. Then in the 1970s, American astronomer Vera Rubin made a discovery that couldn't be dismissed. She was measuring the rotation speeds of spiral galaxies, looking at how fast stars were moving at different distances from the galactic center. According to Newton's laws and Einstein's relativity, objects farther from a gravitational center should move slower. This is how our solar system works. Mercury orbits the Sun much faster than Neptune because it's closer to the Sun's gravitational pull. But in galaxies, Rubin found something completely different. The rotation curve stayed flat. Stars at the edge of galaxies were moving just as fast as stars near the center, sometimes even faster. This violated everything physicists understood about orbital mechanics. There was no way the visible matter in these galaxies could produce enough gravity to keep those outer stars moving so fast. They should be flying off into intergalactic space. The only explanation was that galaxies are embedded in massive halos of invisible matter extending far beyond their visible disks. This dark matter provides the extra gravity needed to keep those outer stars from escaping. It's like having a giant invisible hand holding the galaxy together, preventing it from tearing itself apart through its own rotation. Our Milky Way is no exception. Models based on the motions of stars and satellite galaxies suggest that our galaxy sits within a dark matter halo stretching perhaps 600,000 light-years across, far larger than the visible spiral, which is only about 100,000 light-years in diameter. This halo contains roughly 10 times as much mass as all the stars, gas, and dust combined. It's the gravitational foundation upon which the visible galaxy rests. But what is dark matter made of? This is one of the biggest unsolved mysteries in physics. We know what it's not. It's not ordinary matter made of atoms and molecules. If it were, we'd see it absorbing or emitting light somewhere on the electromagnetic spectrum. It's not black holes, because we detect their gravitational lensing effects when they pass in front of distant light sources. It's not dust or gas, because those scatter light and we can detect that scattering. Whatever dark matter is, it interacts with normal matter only through gravity. It doesn't collide, doesn't clump the way ordinary matter does, doesn't form structures like stars or planets. It just sits there, creating gravity and doing nothing else we can detect. The leading candidates are theoretical particles that have never been observed in nature. Some physicists propose WIMPs, weakly interacting massive particles. These would be particles with significant mass, perhaps tens or hundreds of times heavier than a proton, but that barely interact with ordinary matter except through gravity. They would pass through you, through the Earth, through everything, only occasionally colliding with a nucleus. Others suggest actions, even more exotic and lightweight particles that were originally proposed to solve a different problem in particle physics related to the strong nuclear force. Actions, if they exist, would be incredibly light, billions of times lighter than an electron, but they could exist in such enormous numbers that their collective mass could account for dark matter. There are experiments around the world searching for both types of particles, along with other candidates. These experiments are marvels of engineering and patience. Detectors are placed deep underground, sometimes a mile or more beneath the Earth's surface, to shield them from cosmic rays that constantly bombard the surface and could create false signals. Some experiments use tanks filled with ultra-pure liquid xenon, one of the purest substances ever created by humans. The xenon is cooled to extremely low temperatures and monitored by incredibly sensitive detectors waiting for the flash of light that would occur if a dark matter particle collided with a xenon nucleus. Other experiments use different approaches. Some look for the tiny amount of heat that would be generated by a dark matter collision. Others use crystals of germanium or silicon cooled to near absolute zero, watching for the vibrations that a collision would create. The challenge is enormous because dark matter particles, if they're WIMPs, might pass through a detector for years before a single one happens to hit a nucleus. The idea is simple in concept, but extraordinarily difficult in practice. If dark matter particles exist and are constantly passing through ordinary matter, forming a kind of invisible wind as the Earth moves through the galaxy's dark matter halo, then occasionally one should collide with an atomic nucleus in the detector. This collision would transfer a tiny amount of energy, creating a signal that could be detected. By accumulating these rare collisions over months or years, scientists hope to identify the particle responsible for dark matter. But decades of searching have yielded no confirmed detections. There have been tantalizing hints, unexplained signals that could potentially be dark matter, but none have been confirmed with enough certainty to claim a discovery. Every time a signal appears, it either turns out to be background noise or can't be reproduced by other experiments. This is frustrating for physicists, but it's also informative. It tells us that either dark matter particles interact even more weakly than expected, making them nearly impossible to detect with current technology, or they're not particles at all but something stranger. Some physicists have proposed alternatives to dark matter, theories that modify Newton's and Einstein's equations to explain galaxy rotation without invoking invisible mass. The most well-known is called MOND, Modified Newtonian Dynamics, which suggests that gravity behaves differently at very low accelerations like those experienced at the edges of galaxies. According to MOND, when accelerations become extremely small, far smaller than anything we experience on Earth or in the solar system, gravity becomes stronger than Newton's law predicts. It can also explain the flat rotation curves of galaxies without requiring dark matter, which is appealing in its simplicity. Why invent an entirely new type of particle when you could just modify the laws of gravity slightly? But MOND struggles to account for other observations like the behavior of galaxy clusters, where dark matter seems to be required in different proportions than in individual galaxies. It also has difficulty explaining the cosmic microwave background radiation, the afterglow of the Big Bang, whose detailed patterns seem to require dark matter. Most physicists believe dark matter remains the best explanation, even if we haven't yet identified what it is. The evidence from so many different types of observations, from galaxy rotation to gravitational lensing to the cosmic microwave background, all point to the same conclusion. There's about 5 times as much dark matter in the universe as ordinary matter, and it plays a crucial role in cosmic structure. The European Space Agency's Euclid mission, launched in 2023, is mapping the distribution of dark matter across the universe by observing how it bends light from distant galaxies. NASA's upcoming Nancy Grace Roman Space Telescope will continue this work, creating detailed maps of dark matter's gravitational influence. What these missions reveal is that dark matter isn't evenly distributed. It forms filaments, vast cosmic webs connecting galaxy clusters across billions of light years. Galaxies like the Milky Way form, where these filaments intersect, where dark matter's gravity is strongest. In a way, visible matter is just decoration, condensing along the scaffolding that dark matter provides. Without dark matter, galaxies couldn't form. The universe would look completely different, perhaps devoid of the structures that make life possible. Computer simulations show that dark matter halos are essential for galaxy formation. In simulations without dark matter, galaxies tear themselves apart, unable to hold together against their own rotation and the expansion of the universe. So the Milky Way, this beautiful spiral we call home, is really just a small, visible component of a much larger, invisible structure. The stars we see are like foam on the surface of a dark ocean, supported by depths we cannot perceive. This realization is genuinely humbling. For all our technology, for all our telescopes and equations and satellites, we still cannot identify what most of the universe is made of. We can measure its effects, map its distribution, but we cannot see it or touch it or capture it in a laboratory. It's as if the galaxy is a house where 85% of the rooms are locked and we can only peek through keyholes, inferring what's inside by the shadows on the walls and the creaking of the floorboards. Dark matter may also hold clues to the galaxy's history. The way it's distributed, the structure of its halo, tells us about ancient collisions and mergers. Some astronomers believe they can identify streams of dark matter, remnants of smaller dark matter halos from dwarf galaxies that were consumed. These streams, if they exist and can be detected, would be like archaeological layers, records of the Milky Way's growth written in invisible ink. Right now, as you listen to this, dark matter is passing through you. It's passing through the Earth, through the walls of your room, through your body. Countless particles, if that's what they are, moving silently through ordinary matter like ghosts through walls. You can't feel them, you can't see them. But their collective gravity shapes the galaxy that holds you, shapes the stars that light your nights, shapes the planet that gives you ground to stand on. The existence of dark matter also raises profound questions about the nature of reality itself. If most of the universe is made of something we cannot directly perceive, what does that say about our place in it? Are we living in a thin layer of ordinary matter floating on an ocean of dark matter we can never fully understand? Or will future generations develop new instruments, new theories, new ways of perceiving the universe that make dark matter as obvious and measurable as starlight is to us today? The answer remains to be discovered. But the search continues, driven by curiosity and the knowledge that understanding dark matter means understanding the very foundation of cosmic structure. And speaking of hidden structures, there's another layer to our galaxy that remains invisible to the naked eye, but fills the spaces between the stars. Between the stars, in the vast spaces we think of as empty, there exists a network, a web of gas and magnetic fields stretching across the galaxy like blood vessels in a living body. Astronomers call it the interstellar medium, and though it's incredibly diffuse, far more tenuous than any vacuum we can create on Earth, it contains roughly 10 to 15% of the galaxy's visible mass. More importantly, it's the material from which new stars are born. The interstellar medium exists in different states, different temperatures and densities depending on what's nearby. Cold molecular clouds, where temperatures drop to just 10 degrees above absolute zero, are the densest regions where gravity can pull gas together to form stars. These clouds can be hundreds of light years across and contain enough material to form thousands or even millions of stars. They're the nurseries of the galaxy. Then there are warm regions heated by nearby stars, glowing faintly in radio and infrared wavelengths. And hot regions, blasted by supernova explosions that shine in X-rays with temperatures of millions of degrees. NASA's Spitzer Space Telescope and the European Space Agency's Herschel Space Observatory mapped these regions in detail, revealing a complex, dynamic structure constantly in motion. But there's more to the interstellar medium than just gas and dust. It's threaded with magnetic fields, invisible lines of force that stretch across light years, guiding the flow of charged particles and shaping the formation of new stars. These magnetic fields were discovered through observations of starlight. As light passes through dust grains in space, if those grains are aligned by magnetic fields, the light becomes slightly polarized, twisted in a specific direction. By measuring this polarization across the sky, astronomers can map the orientation of magnetic fields throughout the galaxy. What they found was astonishing. The magnetic fields aren't random. They follow the spiral arms, reinforcing the galaxy's structure. They help regulate star formation by supporting gas clouds against gravitational collapse, at least until those clouds become dense enough that gravity wins. According to research from the Max Planck Institute for Radio Astronomy, these magnetic fields may play a crucial role in galactic dynamics, influencing everything from the birth of stars to the propagation of cosmic rays. The interstellar medium isn't static either. It's constantly being churned, heated, and recycled by stellar processes. When massive stars die in supernova explosions, they blast gas and dust back into the interstellar medium, enriching it with heavier elements forged in stellar cores. This material eventually cools, condenses, and forms new stars and planets. The atoms in your body were once part of this interstellar medium, cycled through multiple generations of stars before condensing onto a planet where life could emerge. The interstellar medium also contains cosmic rays, high-energy particles accelerated to nearly the speed of light by supernova shock waves and other violent processes. These particles stream through the galaxy, passing through you right now, thousands per second, completely unnoticed. Cosmic rays play a crucial role in galactic chemistry. When they collide with molecules in the interstellar medium, they trigger reactions that help form complex organic compounds in molecular clouds. The amino acid precursors, the alcohols, the complex carbon chains that radio telescopes have detected in space, they all owe part of their existence to these energetic particles. The galaxy's magnetic field, threaded through the interstellar medium, acts as a highway for cosmic rays. It helps regulate star formation, can drive galactic winds, and channels hot gas from supernova explosions into the halo, creating what's called the galactic fountain that cycles material between the disk and halo. NASA's Voyager 1 spacecraft, now beyond the Sun's protective bubble called the heliosphere, has been measuring the interstellar medium directly. The data it sends back reveals that the interstellar magnetic field is stronger than expected and the density is higher, meaning our solar system sits in a relatively dense region of local space. We're in what you might call a thick patch of the cosmic gas that fills the galaxy. Recently, astronomers have discovered enormous structures within the interstellar medium called superbubbles. These are cavities hundreds of light years across, carved out by multiple supernova explosions. When many massive stars in the same region all die within a few million years of each other, their explosions can combine to create these gigantic bubbles. They're bounded by shells of compressed gas glowing faintly in radio and X-ray wavelengths. The Fermi bubbles we mentioned earlier, those vast lobes of gamma-ray emission extending above and below the galactic center, may be related to superbubbles, perhaps inflated by a burst of activity from the central black hole millions of years ago, combined with numerous supernova explosions near the galactic center. The galaxy's invisible skeleton, this network of gas, dust, and magnetic fields, is what gives the Milky Way its structure. The spiral arms aren't just collections of stars. They're regions where this invisible skeleton compresses, creating density waves that trigger star formation. The stars are born, live briefly in cosmic terms, and die, returning their material to the interstellar medium to begin the cycle again. In this way, the galaxy is alive in a sense, constantly renewing itself. It's not a static sculpture, but a dynamic system, a cosmic ecosystem where matter flows from gas to stars and back again. The interstellar medium also contains molecules, complex organic compounds floating in the darkness between stars. Radio telescopes have detected over 200 different types of molecules in interstellar space, including water, ammonia, alcohols, and even amino acids, the building blocks of proteins. These discoveries, made by instruments like the ULMA Observatory in Chile, suggest that the chemistry of life may begin long before planets form. The raw ingredients are already present in the interstellar medium, waiting to be incorporated into new solar systems. When our Sun formed 4.6 billion years ago, it condensed from a cloud of gas and dust that was already enriched with these molecules. The complex organic chemistry discovered floating in space, those amino acids and water molecules, they were waiting there in the solar nebula before Earth even existed. The Earth itself, the oceans, the first organic molecules that led to life, all inherited their chemistry from that primordial cloud. In a very real sense, the galaxy's invisible skeleton is also the framework of life. It's the source of raw materials, the nursery of stars, the reservoir of atoms that will one day become planets, oceans, and consciousness. The molecular clouds where stars form are among the coldest, densest regions of the interstellar medium. At temperatures just a few degrees above absolute zero, hydrogen atoms combine to form molecular hydrogen, H2. Molecular hydrogen is difficult to detect directly because it doesn't emit radio waves at these cold temperatures. Instead, astronomers trace molecular clouds using other molecules, particularly carbon monoxide, which emits radio waves more readily and is thought to be well mixed with hydrogen. The most famous molecular cloud is probably the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword. This cloud is actively forming stars right now, and telescopes have revealed hundreds of young stars embedded within it, some still surrounded by protoplanetary disks where planets are forming. The Orion Nebula is relatively close, only about 1,300 light-years away, making it an ideal laboratory for studying star formation. Observations across multiple wavelengths reveal the complex processes at work. Gas collapsing under gravity, magnetic fields channeling material, jets of matter erupting from young stars as they spin and accrete material, and ultraviolet radiation from the hottest newborn stars gradually eroding the cloud that gave birth to them. Eventually, the cloud will be completely dispersed, leaving behind a cluster of young stars that will slowly drift apart over millions of years. This is the fate of all molecular clouds: to give birth to stars and then be destroyed by the very stars they created. It's a cycle of creation and destruction that's been playing out in the Milky Way for billions of years, and it will continue for billions more. The study of the interstellar medium has revealed that the galaxy is far more dynamic than once thought. Gas doesn't simply sit between the stars. It flows, circulates, cycles through different phases. Hot gas from supernova explosions rises above the galactic disk, driven by the energy of the explosion. This gas cools as it rises, eventually reaching a point where it starts falling back down onto the disk, raining down as cold clouds that can form new stars. This process, called the galactic fountain, helps distribute heavy elements throughout the galaxy. Without it, elements forged in stars near the galactic center would stay there, concentrated in the inner regions, unable to reach the outer parts of the disk where our Sun eventually formed. The presence of heavy elements in the Sun and Earth is evidence that this circulation has been operating for billions of years, mixing material from across the galaxy. The interstellar medium also interacts with the galaxy's magnetic field in complex ways. Charged particles, primarily electrons and protons from cosmic rays, spiral along magnetic field lines, creating a pressure that helps support the interstellar medium against gravitational collapse. This magnetic pressure is comparable to thermal pressure in some regions, making magnetic fields an important component of the interstellar medium's physics, not just a minor effect. Recent observations using instruments like the Planck satellite have mapped the magnetic field structure across the entire galaxy, revealing that the fields are stronger and more ordered than previously thought. This has implications for star formation because strong magnetic fields can either inhibit collapse by providing additional support against gravity or channel collapse along field lines, depending on their orientation relative to the gas flow. Now let's talk about one of the most profound mysteries of the Milky Way, a question that brings us back to our place in this vast spiral. The galaxy contains somewhere between 100 and 400 billion stars. The uncertainty in that number comes from how difficult it is to count stars we can't see directly, especially the small, dim stars that vastly outnumber bright ones like our Sun. Most of those stars have planets. This is one of the revolutionary discoveries of the past few decades. NASA's Kepler Space Telescope, which operated from 2009 to 2018, discovered over 2,700 confirmed exoplanets by watching stars for the tiny dips in brightness caused when planets pass in front of them. These observations revealed that planets are common, not rare. Nearly every star has at least one planet, and many have multiple planets orbiting them. A significant fraction of those planets exist in what's called the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planetary surface. Water is crucial for life as we know it, so planets in the habitable zone are our best candidates for finding life elsewhere. Estimates suggest there may be tens of billions of Earth-like planets in the Milky Way alone, worlds with the right size, the right temperature, the right conditions for life to potentially emerge. So statistically, mathematically, based on the sheer numbers involved, we should not be alone. The galaxy should be full of life, or at least have life scattered throughout it at numerous locations. Yet for all our searching, for all our listening, the galaxy is silent. Decades of effort to find radio signals, optical beacons, or any sign of technological civilization have turned up nothing conclusive. SETI, the search for extraterrestrial intelligence, has been listening since the 1960s, scanning millions of frequencies, analyzing billions of signals from space. Every potential detection has turned out to be a natural phenomenon, human interference, or instrumental error. No confirmed signal from another civilization has ever been received. The silence is deafening. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked during a lunch conversation in 1950, "Where is everybody?" If the galaxy is so vast, so old, so full of potentially habitable worlds, where are all the aliens? Why haven't we heard from them? Why haven't they visited? Why don't we see evidence of their existence? The silence suggests something profound. Either life is extraordinarily rare, far rarer than the numbers would suggest, or intelligent civilizations don't last long, or they're hiding and staying quiet for reasons we don't understand, or we're looking in the wrong way and missing signals that are actually there. Some scientists propose what's called the rare earth hypothesis. The idea is that while simple life, bacteria, and single-celled organisms might be relatively common in the universe, complex life like animals and plants requires such a precise set of conditions that it's vanishingly unlikely. You need a stable star that doesn't flare too violently. You need a planet with the right mass and composition, not too big, not too small. You need a large moon to stabilize the planet's axial tilt, preventing wild climate swings. You need a protective magnetic field to shield the surface from radiation. You need a fortunate history free from catastrophic asteroid impacts that could sterilize the planet. All these factors might need to align perfectly, and perhaps they rarely do. Perhaps Earth is genuinely special, not because we're at the center of anything, but because we won a cosmic lottery. If this is true, then simple life might exist on countless worlds, but complex life, the kind that could eventually develop intelligence and technology, might be extremely rare. Others suggest what's called the Great Filter, a barrier that most civilizations fail to pass. This filter could be behind us or ahead of us. If it's behind us, it might be the jump from non-life to life, or from single-celled to multicellular life, or from simple animals to intelligent beings. Each of these transitions might be incredibly difficult, requiring billions of years and extraordinary luck. If most potential life gets stuck at one of these stages, that would explain why we don't see technological civilizations everywhere. But the filter might be ahead of us, which is a darker possibility. Perhaps technological civilizations inevitably destroy themselves shortly after developing advanced technology. Through nuclear war, environmental collapse, artificial intelligence gone wrong, or existential risks we haven't even imagined yet. If this is true, then the galaxy might be full of ruins, dead worlds where civilizations flourished briefly before collapsing, their radio signals fading to silence within centuries of beginning. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to interact. They're observing us from a distance, like researchers studying an uncontacted tribe, following some kind of galactic ethics that prohibits interfering with younger civilizations. Or perhaps they communicate in ways we haven't learned to detect yet, using technologies we haven't discovered, like modulated neutrinos, or gravitational waves, or quantum entanglement, instead of simple radio waves. The galaxy is 13 billion years old, an almost incomprehensible span of time. Civilizations may rise and fall over thousands or millions of years, tiny flickers in cosmic time. Two civilizations might exist in the galaxy at the same moment, but be separated by such vast distances that their signals never overlap. The speed of light is fast by human standards, but the galaxy is vast. A radio signal from a civilization 50,000 light-years away would take 50,000 years to reach us. By the time it arrives, that civilization might have been extinct for 49,000 years. We might be listening for voices that went silent before humans even evolved, or the timing might work the other way. We might be early. Perhaps the Milky Way is just now reaching the stage where complex civilizations emerge. The early universe contained almost no heavy elements. The first stars were made purely of hydrogen and helium, unable to form rocky planets or support complex chemistry. It took several generations of stars living and dying to enrich the galaxy with the elements life needs. Astronomers estimate that the galaxy became suitable for Earth-like planets about 8 to 10 billion years ago. Before that, there simply weren't enough heavy elements floating around. This means complex life in the Milky Way is probably no more than 10 billion years old and likely much younger. Our solar system formed 4.6 billion years ago, relatively late in the galaxy's history. Life on Earth appeared quickly, within a few 100 million years of the planet's formation, but it took billions more years for complex life to emerge. And intelligent life, capable of building technology and asking questions about the universe, appeared only in the last few million years, just yesterday, in cosmic terms. If this timeline is typical, if it usually takes billions of years for intelligence to evolve even after life begins, then most life in the galaxy might still be microbial. Intelligence could be extremely rare, even if simple life is common. This adds another dimension to the mystery. Perhaps the answer isn't that civilizations destroy themselves, but simply that intelligence takes an extraordinarily long time to evolve, longer than most planets have existed in their current stable states. Alternatively, if Earth's timeline is unusually slow, if we're late bloomers, then the galaxy could be full of ancient civilizations that emerged billions of years before us. These civilizations might be so advanced, so different from us, that we can't recognize their activities as technological. They might have moved beyond radio communication, beyond physical structures, into realms of technology we can't even imagine. They could be operating on scales or in dimensions we haven't learned to perceive yet. They could be here, all around us, and we simply don't have the eyes to see them. The search for extraterrestrial intelligence continues through projects like Breakthrough Listen, funded by private donations and using some of the world's most powerful telescopes. These searches scan millions of stars looking for narrowband radio signals or laser pulses that could only be artificial, that couldn't be produced by natural processes. So far, nothing conclusive has been found. But the search has only examined a tiny fraction of the sky at a limited range of frequencies for brief periods. It's like dipping a cup into the ocean once and concluding there are no fish because you didn't catch any. A more comprehensive search will take decades and will require next-generation radio telescopes like the Square Kilometre Array, currently under construction in South Africa and Australia. This array will be 50 times more sensitive than any existing radio telescope, capable of detecting weak signals from thousands of light-years away, signals that current instruments would miss entirely. There's also the possibility of detecting what are called technosignatures, signs of advanced technology that aren't deliberate signals. These might include waste heat from massive energy consumption, atmospheric pollution from industrial activity on a planetary scale, or even megastructures like Dyson spheres, hypothetical constructs that surround stars to capture their energy. NASA has begun funding research into technosignatures, recognizing that they might be more detectable than deliberate transmissions. After all, civilizations might broadcast radio signals for only a brief period, a few centuries, before moving to more efficient communication methods. But they would continue producing waste heat and other byproducts as long as they exist and use energy. The James Webb Space Telescope, though primarily designed for other purposes, has the sensitivity to detect some technosignatures in the atmospheres of nearby exoplanets. Industrial pollutants like chlorofluorocarbons don't occur naturally and would be a strong indicator of technological activity if detected in an exoplanet's atmosphere. You are part of a civilization that looks outward, that builds telescopes and sends messages into the void hoping for an answer. You're living in the moment when humanity first truly grasps the scale of the galaxy and begins to search it systematically for kindred minds. Whether we're alone or surrounded by silent neighbors, the Milky Way remains our home, a spiral of hundreds of billions of stars spinning slowly through the dark, carrying us forward through time. The possibility that we might be alone is both terrifying and awe-inspiring. If no other intelligence exists in our galaxy, if consciousness is genuinely that rare, then it becomes incredibly precious. The universe would be largely unconscious, unable to observe or understand itself except through human eyes and minds. That would place an enormous responsibility on humanity. We would be the only way the cosmos knows itself, the only source of meaning and purpose in an otherwise indifferent universe. Our survival would become cosmically significant, and our extinction would leave the galaxy dark and unobserved once again. But the possibility that we're not alone is equally profound. Contact with another civilization, even just detecting a simple radio signal proving we're not the only ones asking these questions, would be the most important discovery in human history. It would tell us that intelligence can survive its technological adolescence, that the great filter can be passed, that we're part of a larger community of minds scattered across the galaxy, each one looking up at their night sky and wondering if they're alone. For now, we wait and listen. The Milky Way turns slowly, its spiral arms sweeping through space, carrying billions of worlds, some surely capable of supporting life. Perhaps some already host civilizations that are also listening, also wondering, also searching the sky for signals. The silence continues, but the search goes on, driven by curiosity and hope, by the belief that somewhere in this vast galaxy, someone else is looking up, asking the same questions we ask. Now let's talk about something that ties all these mysteries together, a truth that makes our connection to the galaxy far more intimate than you might realize. Every atom in your body has a history that spans the Milky Way. The hydrogen in your water molecules was formed in the first few minutes after the Big Bang, created when the universe was hot and dense enough for nuclear fusion to occur naturally in the expanding fireball. That hydrogen has existed for 13.8 billion years, cycling through stars, clouds, planets, and now living things. The carbon in your cells, the element that forms the backbone of every organic molecule in your body, was forged in the hearts of massive stars that lived and died billions of years ago. Inside these stars, temperatures and pressures were high enough to fuse helium atoms together into carbon through a process called the triple alpha process. When these stars died, some as planetary nebulae and others as supernovae, they scattered their carbon into space. The iron in your blood, crucial for carrying oxygen through your body, was created in supernova explosions, those violent deaths of massive stars. Iron is the end point of stellar fusion because fusing iron requires more energy than it releases. When a star's core fills with iron, fusion stops, the core collapses, and the star explodes. In the intense heat of that explosion, iron and other heavy elements are created and scattered across light years of space. You are not separate from the galaxy. You are made of it. This idea, popularized by Carl Sagan with his phrase, "We are made of star stuff," is literally, factually true. Life on Earth depends entirely on elements that could only be created in stars. Without stars living and dying, without supernovae enriching the interstellar medium with heavy elements, complex chemistry would be impossible. There would be no planets, no oceans, no proteins, no DNA, no life. The story of these elements is the story of cosmic evolution. In the beginning, in the first few minutes after the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. These three elements formed when the universe was still hot enough for nuclear fusion but was expanding and cooling rapidly. This period, called Big Bang nucleosynthesis, lasted only about 15 minutes. After that, the universe had cooled too much for fusion to continue. Tonight, we drift through mysteries written in starlight, through a galaxy that turns without asking permission, keeping secrets older than Earth itself. Above you right now, even if clouds hide it, even if city lights drown it out, the Milky Way stretches across darkness like a river of forgotten stories. That pale band you sometimes glimpse on clear nights, it's only the surface. Behind that soft glow lies a collection of facts so strange, so unexpected, that even astronomers who study it every day still find themselves surprised. The Milky Way isn't just our home. It's a cosmic puzzle box, and tonight we're opening it together. 100 facts, 100 revelations, each one pulling back another layer of mystery. Before we begin, if you find something interesting here tonight, a gentle like or subscribe would mean everything. It's a small thing, but it tells me someone out there is listening, learning, drifting through these cosmic mysteries alongside me. Now settle in, get comfortable, and let's start counting down these mysteries, beginning with the most basic question of all. For thousands of years, people looked up at that band of light and had no idea what they were seeing. The ancient Greeks called it the Milky Circle. Romans thought it was spilled divine milk. Chinese astronomers named it the Silver River. But nobody understood the truth, which is both simple and profound. We live inside the galaxy. We're embedded so deep in one of its spiral arms that seeing its full shape is like trying to understand the layout of a city while standing in the middle of a crowded intersection. The view is blocked by what's closest to you. But the possibility that we're not alone is equally profound. Contact with another civilization, even just detecting a simple radio signal proving we're not the only ones asking these questions, would be the most important discovery in human history. It would tell us that intelligence can survive its technological adolescence, that the great filter can be passed, that we're part of a larger community of minds scattered across the galaxy, each one looking up at their night sky and wondering if they're alone. For now, we wait and listen. The Milky Way turns slowly, its spiral arms sweeping through space, carrying billions of worlds, some surely capable of supporting life. Perhaps some already host civilizations that are also listening, also wondering, also searching the sky for signals. The silence continues, but the search goes on, driven by curiosity and hope, by the belief that somewhere in this vast galaxy, someone else is looking up, asking the same questions we ask. Now let's talk about something that ties all these mysteries together, a truth that makes our connection to the galaxy far more intimate than you might realize. Every atom in your body has a history that spans the Milky Way. The hydrogen in your water molecules was formed in the first few minutes after the Big Bang, created when the universe was hot and dense enough for nuclear fusion to occur naturally in the expanding fireball. That hydrogen has existed for 13.8 billion years, cycling through stars, clouds, planets, and now living things. But these three elements alone can't make much. They're too simple. Hydrogen and helium are gases. Lithium is a soft metal, but there wasn't enough of it to matter. To build the periodic table, to create the diversity of atoms needed for planets and life, you need stars. Stars are cosmic furnaces, fusing hydrogen into helium in their cores through the same process that powers hydrogen bombs, but controlled by gravity and lasting for billions of years. In our Sun, hydrogen fuses into helium at a rate of 600 million tons per second. The mass that disappears, about 4 million tons per second, is converted into energy according to Einstein's equation E equals mc squared. That energy is what makes the Sun shine, but our Sun will never create elements heavier than helium in significant quantities. It's not massive enough. Its core will never get hot enough to fuse helium into carbon. In more massive stars, something remarkable happens. The process doesn't stop at helium. As the core runs out of hydrogen fuel, having fused it all into helium, the core begins to contract under its own gravity. This contraction heats the core, and temperature is everything in nuclear fusion. As the helium core gets hotter and denser, it eventually reaches about 100 million degrees, hot enough for helium fusion to begin. 3 helium nuclei can fuse together to form carbon through a process called the triple alpha process. It's called that because helium nuclei are also called alpha particles in nuclear physics. This process is actually quite delicate and depends on some fortunate quantum mechanical coincidences. If the nuclear forces were slightly different, carbon wouldn't form efficiently and the universe would be very different. Without carbon, complex chemistry and life as we know it couldn't exist. In even more massive stars, stars with 8 or 10 times the Sun's mass or more, the process continues through multiple stages. After the core fuses helium into carbon and oxygen, it contracts again, heats up further, and begins fusing carbon into neon and magnesium. Then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Finally, silicon fuses into iron, nickel, and related elements. Each stage releases less energy and lasts for a shorter time because the physics of nuclear binding energy becomes less favorable as you move up the periodic table. A massive star might spend millions of years fusing hydrogen in its core. It might fuse helium for hundreds of thousands of years, carbon for centuries, neon for about a year, oxygen for just 6 months. But when it gets to silicon fusion, creating iron in the core, this final stage lasts only a few days. The star is racing toward catastrophe, building up an iron core that grows larger with each passing hour. Iron is the end of the line in stellar fusion. This is crucial to understand. Every fusion reaction up to iron releases energy. That's what powers the star, what holds it up against gravity. But fusing iron into heavier elements requires energy input rather than releasing energy. It's thermodynamically unfavorable, so once a star's core fills with iron, fusion stops completely. There's no more energy generation, nothing to support the star against its own gravity. What happens next is one of the most violent events in the universe. The core collapses catastrophically in less than a second. Iron nuclei that were held apart by the intense heat and pressure suddenly find nothing supporting them. They fall inward toward the center of the star, accelerating to a significant fraction of the speed of light. The core, which might have been the size of Earth, collapses down to a ball just 12 miles across in a fraction of a second. This collapse is so violent, so sudden, that it creates a shock wave. The infalling material bounces off the incredibly dense core and rebounds outward. This shock wave, carrying enormous energy, blasts through the star's outer layers, heating them to billions of degrees and blowing them into space at speeds of 10,000 kilometers per second or more. This is a supernova explosion, and it briefly outshines an entire galaxy containing 100 billion normal stars. In those few seconds of extreme temperatures and pressures during the explosion, elements heavier than iron are finally created. Gold, platinum, uranium, thorium, All the elements that cannot be made in normal stellar fusion are forged in the intense heat of the supernova. These elements are created through a process called the R process, rapid neutron capture, where atomic nuclei are bombarded with so many neutrons that they build up heavy elements before having time to decay. The explosion scatters these newly created elements across space. The outer layers of the star, enriched with all the elements created during the star's life and in the explosion itself, expand outward at incredible speeds, mixing with the interstellar medium. This enriched material will eventually cool, condense, and become part of new molecular clouds where future generations of stars and planets will form. Gold, uranium, platinum, all the heavy elements that make up such a tiny fraction of the universe but are so valuable to us, are forged in seconds during these explosions and scattered across the galaxy. Our Sun is at least a third-generation star, possibly more. It formed from a cloud that was already enriched with elements from previous generations of stars. The rocky planets, including Earth, condensed from the leftover material in the protoplanetary disk, building themselves atom by atom from the ashes of long-dead stars. According to research from the Carnegie Institution for Science, the solar system contains material from dozens or even hundreds of different stars. Each element has its own history, its own journey through the galaxy. The calcium in your bones might have come from one supernova that exploded 8 billion years ago. The iron in your blood might have come from a different supernova that exploded 6 billion years ago. The carbon that makes up most of your body's dry mass was forged in a giant star that died before the sun was born. You are a mosaic of stellar deaths, a collection of atoms that have cycled through the galaxy for billions of years, taking different forms, joining different structures, until finally coming together in the pattern that is you. This realization fundamentally changes the way we think about ourselves. We're not isolated biological machines living on an insignificant rock in a random corner of space. We're intrinsic parts of the galaxy's evolution, conscious expressions of cosmic processes that have been operating for 13 billion years. Even the heavier elements beyond iron have specific origins we're now understanding in remarkable detail. Gold and platinum, for example, those precious metals we value so highly, are created primarily in neutron star mergers, some of the most violent events in the universe. When two neutron stars spiral together and collide, the result is almost beyond comprehension. Neutron stars are the collapsed cores of massive stars that have already exploded as supernovae. They're incredibly dense. A neutron star packs about 1.5 times the mass of our Sun into a sphere only about 12 miles across. That's density beyond anything we can really imagine. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity at the surface is so intense that if you dropped something from a height of 1 meter, it would hit the surface at millions of kilometers per hour. When two of these objects spiral together in a death dance, orbiting each other hundreds of times per second in the final moments before collision, they emit gravitational waves, ripples in the fabric of space-time itself. These waves carry away energy, causing the orbit to decay, drawing the neutron stars closer and closer together until they finally merge in a catastrophic collision. The explosion creates what's called a kilonova, an event that can briefly outshine an entire galaxy, though not quite as bright as a supernova. The collision is so violent, the temperatures and pressures so extreme, that neutrons are literally crammed into atomic nuclei by the quadrillion. Atomic nuclei capture neutron after neutron in rapid succession before they have time to decay, building up heavier and heavier elements through the R process, rapid neutron capture process. This is where gold comes from. Platinum, uranium, thorium, all the heaviest elements in the periodic table are forged primarily in these seconds of cosmic violence. The material is then blasted into space at a significant fraction of light speed, glowing with the heat of radioactive decay as unstable nuclei settle into stable configurations, producing that characteristic kilonova glow that astronomers can detect from billions of light years away. Every atom of gold on Earth, every gold ring, every electronic contact plated with gold, every gold dental filling, came from neutron star mergers that occurred billions of years ago, somewhere in the primordial Milky Way or in dwarf galaxies that were later consumed by our galaxy. These mergers are extraordinarily rare. They might happen in our galaxy once every 10,000 years or so. But over billions of years, they've occurred often enough to seed the interstellar medium with detectable amounts of these precious heavy elements. The detection of gravitational waves from merging neutron stars on August 17, 2017, was a watershed moment in astronomy. For the first time, we detected the same event through multiple channels. Gravitational wave detectors felt the ripples in space-time. Then, about 2 seconds later, gamma-ray telescopes detected a burst of high-energy radiation. Hours later, optical telescopes saw the kilonova beginning to glow. Over the following days and weeks, astronomers observed the characteristic spectrum of heavy elements in the explosion's light, confirming that neutron star mergers do indeed produce gold, platinum, and the heaviest elements. This single observation confirmed theories that had been developed over decades but never directly tested. It showed that neutron star mergers are cosmic forges, foundries where the heaviest elements are created. It demonstrated that gravitational wave astronomy works and can tell us things we could never learn from light alone. And it proved that some of the rarest, most violent events in the universe are also essential for creating the elements that make up our world. Even the lighter elements have remarkable stories. The hydrogen in your body is primordial, formed in the first minutes after the Big Bang. It has existed for 13.8 billion years, cycling through stars, nebulae, comets, oceans, rain, and now your cells. The oxygen you breathe was created in massive stars, fused from helium and carbon in cores heated to hundreds of millions of degrees. When those stars died, they expelled oxygen-rich outer layers into space, where it mixed with hydrogen to form water molecules that eventually condensed onto Earth. The nitrogen in your DNA, crucial for the structure of genetic code, was created through a process called the CNO cycle, where carbon, nitrogen, and oxygen participate in a chain of nuclear reactions that convert hydrogen into helium while regenerating the carbon. This process operates in stars slightly more massive than the Sun. The phosphorus in your bones and DNA came from the silicon-burning phase of massive stars created in the final days before those stars exploded as supernovae. Phosphorus is relatively rare in the universe because its creation requires very specific conditions that only occur briefly. The abundance of elements varies throughout the galaxy in ways that tell us about its history. Stars near the galactic center tend to be more metal-rich because they formed from gas enriched by many previous generations of stars. Stars in the halo and outer regions are metal-poor because they formed earlier from less enriched gas. Our Sun sits in a sweet spot with a metallicity that's roughly average for stars in the galactic disk. This metallicity was crucial for the formation of rocky planets. A star with too little metal cannot form substantial rocky planets because there isn't enough solid material in the protoplanetary disk. Everything would be hydrogen and helium gas. A star with too much metal might form planets that are too large, becoming mini Neptunes with thick hydrogen atmospheres rather than Earth-like worlds with solid surfaces. The Sun's metallicity suggests it formed from gas that had already been enriched by at least one, probably several generations of stars. The supernova explosions that created the heavy elements in your body occurred before the solar system existed, perhaps hundreds of millions of years before, giving the enriched material time to mix thoroughly with the interstellar medium before being incorporated into the solar nebula from which our sun and planets formed. Some of those elements preserve traces of their specific origins. Certain isotopes, varieties of elements with different numbers of neutrons, can only be created in specific types of stellar events. By measuring isotope ratios in meteorites, scientists can identify the contributions from different sources: red giant stars, supernovae, neutron star mergers, even cosmic ray interactions in space. This cosmic archaeology reveals that our solar system incorporated material from many different stars, each contributing different elements and isotopes. We are not descended from a single stellar ancestor, but from a whole community of stars that lived, died, and enriched the galaxy before the sun was born. The connection between humans and the galaxy goes deeper than just atomic composition. The laws of physics that govern stellar fusion are the same laws that govern chemistry, biology, and ultimately consciousness. We are not separate from the physical universe. We are expressions of it, patterns that have emerged naturally from the same fundamental forces and particles that create stars and galaxies. This unity is both humbling and exhilarating. It means we belong here, not as alien intruders on an indifferent world, but as natural outcomes of cosmic evolution. The galaxy has been building toward complexity for billions of years, and we are part of that story, perhaps one of its most interesting chapters. As astrophysicist Neil deGrasse Tyson once said, "We are not just in the universe, we are of the universe, and the universe is in us." Every atom in your body was once floating in interstellar space, part of that invisible skeleton we discussed earlier. The story continues inside you, around you, above you. The Milky Way isn't just your home, it's your ancestor, your origin, and in a very real sense, it's you. The rotation continues, unbroken since the galaxy's beginning. The spiral arms sweep through space, carrying their cargo of stars and planets and dust and dreams. The dark matter halo holds everything together with invisible hands. The interstellar medium flows and cycles, birthing new stars from the ashes of old ones. And somewhere in all this motion, on a small rocky planet circling an ordinary star, consciousness has emerged, capable of understanding what it's part of, capable of looking back at the galaxy and recognizing itself in the patterns of starlight. We have mapped the spiral from within. We have measured the black hole at its heart. We have identified the dark matter that holds it together. We have traced the chemical evolution that makes life possible. And we have begun to search for others who might have done the same. But for all our knowledge, the Milky Way remains mysterious. We don't know what dark matter actually is. We don't know if we're alone. We don't fully understand how galaxies form or evolve. We don't know what the far future holds, what will happen when Andromeda arrives, or whether humanity will still exist to witness it. These unknowns are not failures of science. They're invitations, calls to future generations to keep looking, keep questioning, keep exploring. The Milky Way has more secrets waiting to be discovered, and we've only begun to scratch the surface. Each answer we find opens new questions. Each mystery we solve reveals deeper mysteries beneath. Thank you for drifting through these 100 mysteries with me tonight. If this journey sparked your curiosity or brought you a moment of wonder, a gentle like or subscribe would mean everything. And please, leave a comment telling me which fact surprised you most, which mystery captured your imagination. I love hearing from listeners across the planet, all of us looking up at the same galaxy, wondering together. Now rest. Let the stars turn above you. Let the galaxy carry you gently forward through space and time. You are made of the Milky Way, and the Milky Way is made of countless mysteries, each one waiting to be understood. The spiral holds you, and it always will. Sleep well, stardust.